Okay, so next up we have Charlie Murphy, who's going to talk about semantic-guided synthesis and how to verify solutions for these problems.
Hello, thank you. So yeah, today I'm going to be talking about our paper. This is joint work done with collaborators at University of Wisconsin-Madison and UC San Diego, and this is work that I did before joining Amazon. So this work is sort of inspired by the desire to do language-agnostic program synthesis. And so let's go over a few examples of what we mean by synthesis and sort of the setup that we're trying to work with. So you might try to synthesize a term from this language, and implicitly, when you're doing this synthesis, you're sort of synthesizing things against a known semantics for, SemGuS or SMT terms, and with a given specification. For example, this prose that says we want to try to compute the maximum value of two variables, x and y. And so other domains, such as imperative languages, you've got this search space here that says I've got imperative, I've got a looping program that does some sort of increments and decrements on the variables x and y. And again, the semantics is sort of implicitly like as an imperative or C-like language. And the specification of your program might be like you're looking for a program that doubles x and stores it in y. A different domain might be that you're trying to synthesize a regular expression. Again, there might be many different kinds of semantics for it, such as like the matrix-based semantics. You don't have to worry about what that is. And then your specification might be saying that I want to accept all strings that begin with 1 and end with 0. And finally, we might try to do something like synthesize an SQL query with the standard semantics of SQL. And the specification that says, just return all rows within some given table when a column of that table is positive. So as a user of synthesis, what might be really complex and really hard to use synthesis tools is that when you actually try to do synthesis, there's different tools for different languages, and they each have their own input description, and the tools aren't very usable. And so what you would like is sort of a single interface for actually writing your synthesis problems. And so this is what's accomplished by the Semantics-Guided Synthesis framework, which requires that you provide a syntax, semantics, and specification. And so the SemGuS framework, has these three components. Going back to like the first example, it's got a search space, a grammar defining the search space of programs. You have to provide a formal semantics for every element in your syntax. And so this actually looks like something that's inductively defined over your grammar. And so here this says that variable x is just returns the value of x. Variable y similarly returns the value of y. And then the value of E1 plus E2 is inductively defined by the value of E1 and the value of E2 and just summing them. You can do that for all the other elements in the grammar, but I'm not going to bore you with all that. And then if you have a specification, it's defined as a logical formula that's defined over the semantics of the program that you're looking to search for, in this case, max. And this just gives a specification that says max is the thing that you... This here says that the program that we're looking for, max, returns some value r, and that value is greater than both x and y and equal to one of them, sort of the standard definition of max. So now that we've got this, we've defined a SemGuS framework, a SemGuS problem, and we can provide that to a tool, and we're ready to start trying to define a synthesizer that takes as one of these inputs. And for now, I'm just going to assume that we're trying to build a synthesizer that uses really simple algorithm, like enumeration-based algorithm. And so the enumeration will take your search space, enumerate some program from it, and now we've come to actually a really tricky part is how do we verify that this program is actually correct if we just enumerated it blindly? And the real focus of this talk is actually how do we verify a program when the input to your verifier is also the semantics of the language in which you're doing verification in. So here we're trying to prove that the program P satisfies the specification when interpreted in the semantics that the user provided to you. And so this talk is just trying to figure out what do we put in this box here to make this actually work. And so when the specification is just example-based, this is already done by the original work on SemGuS. But what happens when we want to use quantified logical specification? This is work that, hadn't been done until my paper. And so let's go ahead and talk about this through a couple of examples. So here's, going back to the original example, the max problem. Let's see how we might try to figure this out. As many of you might know, this program here implements max. So we want to try to verify that this program satisfies the specification, which it will. But how can we prove that? So here, what we can do is actually try to find a closed form solution for this if state, for this just if then else expression. And if we do that, it equals to this SMT term. We can say the semantics of this is equal to this. That's pretty easy to see and pretty easy to figure out because this term is non-recursive. So it has a very easy way to compute the closed form solution by just iteratively defining, going from the leaves of the grammar and building up the semantics of it into just a closed form solution. And then what we can do is take this semantics for the program and substitute it into the specification for the dummy, so for sort of the placeholder of our program max. And we just substitute this. And now we have an SMT formula that we can just give to an off-the-shelf solver. However, this doesn't always work. It only really works for non-recursive programs like we saw here. But this allows us to plug in just a little bit of what that should be in that box. And the first is can this be encoded in SMT? So is this a non-recursive function program? And if the answer is yes, well, we just encode it using SMT and sort of the thing using the encoding that I hinted at in the example. And if it satisfies that formula, well, great, you're done. You've produced a program that satisfies your specification. If not, you just have to go back and re-enumerate. Now, what if the problem isn't encodable in SMT, such as when you want to synthesize a recursive program? And so if you want to do that, we have to sort of figure out some other encoding. And so for this, let's go back to the second example that we looked at, this imperative program here that we want to try to compute the double of x and sort in y using just increments and decrements in a loop. So here, the semantics of this is fairly standard. You got the while false rule and the while true rule. I don't expect you to read them, but these are just really standard semantics that's sort of just inductively defined, as I said. And then the specification here, let's assume that we're looking for partial correctness. And so this is just saying that the input state and output state represented by the prime variables, that our desired function double takes, if it terminates on the input xy, it does so in the state x prime, y prime, and that the final value of y is equal to twice the input value of x. So that's exactly what sort of one interpretation of what that prose might mean. And so we can take this and start trying to figure out how do we verify that the following program actually implements the specification. And intuitively, this is the correct program, but how do we prove it? Well, what we might actually realize is that the semantics, because they're defined in such an inductive way, that the semantics are all constraint horn clauses, and that the specification, because the semantics only appears in a negative location, that this is, again, a valid query to give to a CHC solver. And the nice thing is that for queries like this, they can be solved using a CHC solver. And so, sort of as I'm hinting at, this only works for some specifications, ones in which the semantic relations appear negatively in your specification. So this sort of corresponds to the class of partial correctness. So we sort of get to fill in just a little bit more of this box and saying if it's a partially correct specification, we can then encode this into CHCs and verify it using a CHC solver. And so just like you did with the SMT case, if it says yes, you're done. If no, you repeat. Now, the last question is, what do we do if it's not encodable into CHC? Well, that means, so that sort of corresponds to what do we want to do if we want to try to prove total correctness of a program? So the answer here is that let's go ahead and look back at the same example again, but instead consider a slightly different specification. This is a form of total correctness. It says that for every input state, there needs to be an output state, that the program goes from the input state to the output state, and the final value of y is equal to 2x. So this is just flipping the definition, saying that there has to exist this execution here. So now that we know, now that we sort of look at this is not encodable into constraint horn clauses, and so we can't just use the same exact method that we did last time. And sort of the real intuition behind this is that the semantics aren't, exactly defined the same exact semantics as CHCs. Instead, it's exactly the least solution to these rules, or like the least fixed point of this. And if we want to really reason about every possible query or specification from our semantics, we need to really use a logic that supports least fixed points as sort of a first-class citizen of the logic. And so we can actually translate this into a more general fixed point logic, such as µCLP. And so the while rules sort of just gets simply translated into this least fixed point equation in µCLP, a logical fragment described in POPL 2023. And so here it just combines the two rules for while, the while false rule and the while true rule, into saying that the semantics of while is defined as the least solution to this definition, along with all the other rules for defining the rest of the elements in your language. And you can do that you can do this translation like grammar point by grammar, grammar element by grammar element to get an entire µCLP formula for your semantics. And then you just combine that with your query and you can give it to the µCLP solver, which is great. And so now we finally have the last component that says if it's neither SMT encodable or CHC encodable, it is µCLP encodable because it's just general enough to support every SemGuS verification query. And again, if it says yes, you've got a program. If not, you have to re-enumerate. And now we've sort of got a closed loop of our verifier and synthesizer enumeration that sort of can solve or verify any possible SemGuS problem just using existing logic solvers by doing various like encodings and just translation from one logical fragment to another. So now we have a verifier for solving any possible specification with quantified logical specifications. So one thing when we were implementing this is that we noticed that we don't make full use of the µCLP fragment of logic. In fact, we only need to use least fixed points, where µCLP allows arbitrary alternations of greatest and least fixed points in its definitions. And so that got us to ask, is there any meaningful extension of SemGuS that actually makes a greater use of µCLP's capabilities? And the answer to that was actually yes. We could modify our definition of semantics to get it closer to µCLP, and this allowed us to represent not just functional synthesis problems, which the original SemGuS framework only supported, but also reactive synthesis problems like controller synthesis or Buki games or stuff like that. I'm not going to give an explanation, an in-depth example of here because of time, but the last part I want to talk about is like sort of evaluating this. And so we actually evaluated this on a number of benchmarks that we collected from the SemGuS GitHub, as well as some new problems for the reactive synthesis encodings. And so they come from 9 different domains, showing how sort of like general this technique is by just using logic. So it includes encodings of SemGuS problems, imperative array manipulating programs, imperative functional integer manipulating programs, Boolean expressions, regular expressions, a DSL for representing scorecards, as well as several reactive synthesis domains like controllers using LTL expression, LTL specifications, strategy for using robots, and also like these reachability Buki games that are very common in reactive synthesis. We sort of evaluated our verifier alone without synthesis by for each synthesis problem having one problem that satisfied one program that satisfied one program that did not satisfy each specification or problem. And then sort of to point out of the 730 verification queries that we tried, our virtual best solver solved 709 out of those, while like each one solved around 525 to 575 of these different encodings. So the SMT encoding, the CHC encoding, and the general µCLP encoding. And so we also broke it down per benchmark. I don't expect you to really read this whole table, but It's just that it worked pretty well for most of these domains. And, generally, if something could be solved as an S&T theory, you should solve it using that rather than CHC, rather than µCLP, because of how the solvers sort of scale to those kinds of complexities. And then finally, we evaluated this in a synthesis and an enumeration-based algorithm, like we were sort of showing in the presentation. So we incorporated an existing enumeration-based solver for SemGuS by just replacing its verification routine with our own verifier. And we were able to solve 135 SemGuS problems with logical specifications, 74 of which could not be solved by any other existing solver for SemGuS. And I just would like to thank my collaborators and let you ask any questions. Thank you.
Questions? So did you manage to compare against reactive synthesis solvers?
So we did not actually do any synthesis techniques for reactive synthesis, as the underlying SemGuS solver, like enumerator, doesn't actually work for the extended we had to extend the framework to allow even writing down or encoding these other reactive synthesis solvers, and we just didn't have the ability to change the solver, the enumerator to handle the enriched framework.
But then your evaluation had controllers and games.
Yeah, so this is the verifier, which is able to do these things. Okay. What we expect is that if you were to try to update this, we wouldn't scale as well as specialized reactive synthesis solvers. And the key point here is that if you've got things that are kind of weird and weren't, solvable in these like pre-existing solvers, like these specialized domains, that you could actually implement this and get something like a baseline for these other things. And so this is sort of like designed to be used for like lower resource problems. And so at this point, it really only scales to sort of smaller programs. If you get like to 100 lines of code, it doesn't really work.
Okay. And do you have ideas on how to scale to beyond?
Yeah, so the idea is like trying to take sort of like these domain specific, so just as we did with saying this is an SMT-like problem, this is a CHC-like problem, using sort of inspiration from domain specific techniques to try to generalize those and sort of like what's the essence of what's required from the semantics or what's required from the syntax in order to implement these techniques, like sort of invariant generation techniques or like type-directed verification techniques, and try to sort of apply those, like generalize those, and say, hey, if it's like this kind of problem, we can apply this more domain-specific technique.
Makes sense. Thank you.
Thank you.
And okay, so let's thank Charlie again.